Yep. All right. Today you've been basically talking with Pani Nadia for the topic for convolutional neural networks and things like the deep neural nets architecture, inceptions, VGG, AlexNet, LinNet, etc. Those are quite outdated architectures, but it is very important to actually know what's going on and to realize that all the recent state-of-the-art best models, best practices, approaches that beat every single benchmark that you can see in papers with code, for instance, image classification, is all based and built upon all the previous works. That's very important to realize. So basically, if you go into ImageNet, there's that's part of the slide. I've been taking a peek at the lecture today with you, and this is basically the slide that comes on the evolution on different convolutional and not only convolutional architectures for ImageNet. And the thing is, if you have any questions in particular to pertaining to the lecture, to deep neural nets, architectures, inquiries, anything, you can ask them right now or just interrupt me whenever you feel like it. If not, I'll just dive straight into the practice assignment. So as far as I know, as far as we've briefly synced up with Pani Nadia, basically this part of the assignment is not necessary right now. It's optional because vision transformers or ViTs have not been properly introduced from our side, so you are not obliged to complete this like in a week's time. A bit later, Dr. Nadia, Dr. Schwam, sorry, I'm going to refer to our lecture as that. Dr. Schwai is actually going to introduce ViT models and vision transformers, the concept of attention in computer vision, especially in the next week, and then you'll be then obliged to complete this task. For now, let's just focus on the practical assignment or just the transfer learning for image classification. Basically, last week we had the same data set. You are supposed to work on the same data set from the last week. Let me see. This one, the STL10 with 10 classes and 5,000 images on train, 8,000 images on test. It's a pretty tiny data set. It's very important to be like cautious here and to actually not overextend on the model, not overfit on such like tiny amount of data, comparing to like recent and more advanced data sets on image classification and not only like in computer vision in general. And basically, there's this resolution problem as well. There's only 96 by 96 pixels and like 3 color channels, of course. And you are tasked in the assignment, you're tasked to classify the very same data set that you've been working on in a big Word assignment last week. So you have to do absolutely the same kind of processing, but you are not to write a lot of unnecessary modules in a classical approach, like histogram extraction, key points detection, histogram normalization, and then SVM on top of that. Instead, you're supposed to use some existing architecture like ResNet, which is basically the reception, the ResNets. Yeah, this is, I don't know if you've been into much detail on the ResNet, but ResNet and EfficientNet are pretty much, effectively they're the same. EfficientNet is just much more optimized, and ResNet has basically a very key concept, a very vital concept that enabled the birth of a true deep learning. By true deep learning, I mean like deep neural nets with 100 layers or deeper or more. And they have a concept of residual connections, like the residuals or like skip connections. So basically, if we go ahead and Google architecture of ResNet and go into images, there's this somewhat scary of an image, but let me see if I can, yeah, seems good. So basically, the architecture itself resembles very much like something very similar to VGG, with convolutional blocks being swapped by pooling layers, then convolutional blocks and pooling layers, activation functions all over the place. But there is a big difference here. Like VGG is on top, the very top row. What's going on? The VGG is at the top row. Basically, this input, right, from right to left we're going. So I'm actually going to cut this out and do this in Paint. Can be much simpler. So in this very specific case, we are trying to imitate the same pipeline as VGG, basically flowing left to right. Let me select the color. So this is our direction of processing and input, this way. This is our output, right here. Like I'm going to be denoting outputs here in the in this section, kind of like with green, with the salad color. The input though, yeah, this is the output, basically the fully connected feed-forward pass. This is the output here. This is the output here in ResNet. No, actually, this basically. These are very similar. These architectures are very similar, but there's one big key conceptual difference. It's these arrows. But we're just going to briefly talk about this all and then get back to the home assignment. And for VGG19, there's obviously the convolutional input. There's 3x3 convolutions. Let me see if I can zoom this in. There we go. So 3x3 convolutions twice, then there's a pooling that reduces the whole W and H dimensions by 2, by a factor of 2. And then there's further convolutions which increase the feature maps or the channels count by the further magnitude of by 2, so 64 after first pass. Let me do this. And then 128 after the second pass, and then it continues like subordinately swapping with these pooling layers, pooling by 2, so the resolution reduces. It's becoming more tiny, I guess, but the number of channels is basically increasing. These red signatures for 256, even more convolutional operations, kernels are being applied, and then there's there's also pooling and more convolutions and more pooling, more convolutions, and yeah, they also indicate very importantly. Let me see if I can rotate left by 90. Yeah. So they have output size, input size. So it was supposed to be 2 to 4 here. 2 to 4, just the typical usual ImageNet picture, post-ImageNet processing picture, image frame. And then it's reduced by the factor of 2, like 112, but the maps are actually, so basically, this way we are decreasing. We decrease here by factor of 2, 56, then 28, then 14, and then 7. So basically we are reducing our dimensions, we're becoming tinier. Step by step, we're just making the image look less and less appealing, kind of as a human being. But in contrast, we do expand on the size of channels or feature maps, something that the convolutional operations extract from the image. And this way we're going up. Oh, sorry, that's a bit wrong. This way we're going up. We're going increase 128, 64, 128, 256, 512, and this already at this stage. This is a kind of a pseudo important step, kind of important actually. They do not go over like over to 10 to the power of 2 to the power of 10. They do not go over to 10 1024. feature maps, but they just keep the same stride and the same padding, so to not expand even further on the scale of like depth. So we do not go in depth anymore from this stage. We start going in like in depth, generating a thicker representation of the image, and at each kind of stage, the resolution decreases, the depth increases. This is kind of like the mapping, final pre-mapping, post-feature collection state. And then in the end, there's like this last pooling layer, last output size 7, and then in this this particular case, there's a fully connected feed-forward part of the network that consists of 3 layers. So basically, what it does is basically, I'm actually kind of I have lied to you. They do increase this even further. So this doubles up as well. So they receive 1024 feature maps times 4 as per each of these layers. 1, 2, 3, 4. So they just stack them up. They flatten them, and they have 4096 neurons. And after this, they just apply fully connected. I don't know, they use something like sigmoid or softmax, and softmax is used here, softmax, I will just indicate this here. And then this is a linear mapping function, the first one and the second one. And once this is done, they apply a softmax and transpose the weights that are coming out of this one. There's a weight matrix, of course, and they just transpose this weight matrix, even though it's kind of like one-dimensional, but they just apply softmax on it. This is something like 1/1 divided by exponented negative exponent to the power of something. I always forget. You can go this up easily. The softmax function. So they renormalize this 1000 weights into 1000 probabilities. And then you get like this long list of the output. Output's going to be, once again, this solid color. So they have this top K, right? Let's just put this top K. So top K confidences by the model that the picture or the image belongs to some class. There's like one class, the most confident one has like 37% chance that it's a frog. So just a creature, just an animal. And then there's something very similar to a frog, but not quite. Maybe some different kind of like small peculiar animal as well. And this goes on, and basically in ImageNet they have like this 2 benchmarks. They have the top K or top N accuracy, usually top 5, where N is 5. So they just name 5 accuracies. For top 5 accuracy for different classes, and the correct class prediction, the correct label, for instance, like a car, is supposed to be somewhere here or here, or any of these positions. If it makes it to top N, it's the correct prediction, otherwise it is not. And there's also more like strict, more realistic evaluation, let's say, is the top one. So the top one is only the label is considered to be, the predicted label is considered to be correct only when it completely matches the right label and it's actually on the first place. So you're doing something similar to this, pretty similar, but let me see. But let me just also explain the ResNet ideologically, because we, as I've seen through the course of the lecture from the previous previous period, you have not been in depth on the ResNets, so I'll just quickly introduce it, and then you can catch up if you want on your own. There's a 34 like level, 34 layer constituent predefined recipe, and it was created on the basis of VGG and like overall on the previous convolutional architectures. So it's just more stacked, more like dense, I would say. And there's this same pattern. There's different convolutional kernel here, much more inefficient one in my opinion, 7x7, and just pooling 3x3 convolutions. 3 by 3 convolutions with a feature count, channel count reduction. And we go further, more feature extracted. It's a very deep network, very dense. And this may be a problem. There's an average pooling in the end. So contrary to this approach on the left, the VGG 19, they do not as often insert this pooling operation, which reduces the resolution of the feature maps of the image itself that's being processed. And this just causes the feature maps of high resolution to stack up, and once they do, that can lead to very serious problems with memory, with training, with the whole network converging. This could be bad. So researchers from, I don't quite remember who was like the key author, this kind of shame on me, but in 2015 they came up, like 16, 15, they probably 16 or even like finalized version, they came up with the concept of residual connections, or just they introduced the architecture of ResNets. So they took this architecture in the middle, the 34-layer one, very dense one, and they added these it's kind of like these stepovers over some of the blocks. And this basically, in very plain language, these residual connections or skip connections, they have a function here. They have a function like like a plus, and there's also a probability here. Or it's just not the plus. I don't quite remember. Yeah, I think it could be a plus, could be something else, but it just depends. So at this point, when the network flows, so just input image, perform this block. Good. This is good. Then we do a pooling. Nice. Then we can come to this intersection, to this very tiny point where there is either an option to go into the first convolutional block or to skip over, to step over. And there's this like certain amount of probability with which the model during training can just skip over, use this path, and like skip 2 blocks. And then there's also probability it can skip more blocks. And by skipping, I mean completely ignoring any operations that lie within any convolutional kernels, any weight updates, any activation functions. That basically it makes a network much more sparse. So this can be a bit randomized, you know. You can train like sometimes it can be 3 in a row and only start training here. But this is like I don't remember what dashed ones means. So yeah, I think I remember now. Dashed oversteps, they mean that basically there is a necessity. They have like different probability because the new stage begins with different amount of feature maps, and I think probably the probability is supposed to be less in this one, this first part of the new like section. And in the end, can skip like hop over many some of these parts of the network, or like 30% of the blocks can be skipped, sometimes 50, sometimes less, much less than that. But basically, the whole idea is to make the neural nets. What this trick does, it allows the network not to overfit, not to like get too much over memory consumption on the feature maps. It also does allow for a faster training, faster inference speed, better convergence, and generally makes the network more robust. So this is why this architecture, ResNet, was like a big boom in computer vision. Continues like a good successor to AlexNet back in 2012. ResNet was an absolute miracle, and based on this architecture, based on different like depths, so you can basically also check out like ResNets. There are different types of ResNets. ResNet types. There's like depth. ResNet 18 layers. 34, the one I just showed. ResNet 50. ResNet 101. ResNet 110, 152. Well, the most common ones are, of course, ResNet 18, ResNet 152, and ResNet 101. ResNet 50 is more or less common. This is quite common, but a bit less than the other ones. These ones are quite rare. And So basically, you can see that this kind of ideological approach of residual connections, skip paths, allows the very deep networks to be trained, and that's astounding. Basically, the the architecture was improved over time and became something known as WideResNet. You can have a look at the paper. You can have a look at PyTorch tutorial instead. So they have ResNet bottlenecks, basically this plus sign where they just skip. They have the identity function there. They have yeah, just how to play with the model. I'll show this for the practice. And these networks are even more sparse. They're not as deep, but they're still kind of like they go in with. They use the concept of inception modules from GoogleNet, and they also train quite well. They're like most libraries, most deep learning frameworks right now. Both TensorFlow, PyTorch, very often they are used to evaluate some of the data sets and just to modify on them, try new concepts, new mechanisms in this architecture, like specifically on WideResNets. So this is the first architecture, ResNet, basically summarized very briefly in a matter of 20 minutes or something. There's also EfficientNet. EfficientNet is basically a very optimized in terms of time and space, time complexity, training time, space in terms of less memory being used, and better inference speed version of ResNet. It's very much refined. The people, the researchers who published the paper, they spent so much time tweaking around with parameters, trying to overcome different bottlenecks, and increase the usability of this approach of ResNet in production, not only in research scenarios but in production. This was also a big hype. Back in 2018, 2019, these networks were all over the place. And there are pretty much also the same level of difficulty to use as ResNet. So you just select a different backbone, different weights once you will be training them for your home assignment. So you might give it a shot. And ViTs also, this is like you only pick one of these. ViTs, yeah, we have not talked about them. Not going to talk about them right now, even though I would really like to. Don't have that much time. We're talking about the home assignment. This is the Vision Transformers most recent peak and the trend, but it's a very unrobust model, kind of like a robustless model. A very powerful one, has much bigger head, like back then when it came out in 2019, 2020. It had much better potential to get better accuracy on different benchmarks or different metrics, but it was very slow and very awkward. It trained very poorly, and there were a lot of issues. But we're not talking about vision transformers today. Just anything of your liking. You can use VGG. You can use GoogleNet if you find it. Any version of ResNet, EfficientNet. Just make sure to not overfit in this data set. This data set is quite tiny, only like 5,000 training images, and you have to be careful. So let's continue. Yeah, if this is even mentioned here, taking into account the small data set size, you have to use something called pre-trained deep learning modeling. So when you basically do not reinvent the wheel, when you fetch an architecture from either PyTorch or TensorFlow or whatever framework you like, you download the pre-trained weights for ImageNet, right? Because there's even a tip here. The images were acquired from labeled examples on ImageNet. So if the model, supposedly, like there's this discrete mathematics task, if the big model was trained on the whole ImageNet dataset and has weights from there, 1,000 classes, this whole huge area, it pretty much is supposed, it must have the same amount of information to describe and to correctly get features, retrieve features from these images, from these 10 classes, and to correctly classify them. You just have to make sure you are using the right weights, the right architecture for them, and that you change the last part of the pipeline, which is the top layer. The top layer, once again, I'm going to go back to this paint image here. The top layer is anything that is divided or just separated by this green color. So the output phase, or the top layer, or a feed-forward part of the network, this all it does is basically it finishes pre-processing for the images, and once all the linear functions have been applied, everything has been mapped, everything has been flattened, it just transforms via softmax. It does transform these weights into an appropriate amount of classes. So in this case, there is FC 1000, right? This FC 1000 means this network was supposed to train on an ImageNet with 1000 classes. You gotta make sure you switch this kind of like head of the network. You switch this to something like FC10. So the same layer, nothing has to be changed pretty much. You just keep everything the same, and you just change the number of output neurons to 10, not neurons but classes, and then it just automatically readjusts the pipeline. And what is more, I think if you are using PyTorch, and probably TensorFlow as well, I'm not sure about TensorFlow, but yeah, TensorFlow probably yes. Yeah. If the model was trained on ImageNet, for instance, casual ResNet 18, and it has resolution 224 on 224, then if you feed the ImageNet data, like this data, to the network, this is going to finally accept it, process it, and give you good output. However, there's another case when you are using some toy data set like this one. It has a different resolution, 96 by 96. It's a color scale, so yeah, by 3, of course. This means no matter how badly we want, without like some extra very sophisticated modern techniques like super resolution, we will not be able to match this image input. But hopefully and gladly for you, the under the hood API of PyTorch, Torch Vision models, and TensorFlow Model Zoo, they both they receive this input. Once you receive, you compile the model. Like before you can compile, you explicitly specify the resolution of your input images, like the one image, 96 by 96 by 3. And then this pipeline, this whole architecture of ResNet is getting adjusted because, of course, it is very intuitive and self-explanatory that a different amount of depth is required for this image and for this image. And same goes for kernel size, some certain parameters or like specific techniques as dropout or anything that's to your liking in the neural architecture, it automatically gets adjusted, and you get the ready-to-go model like this one that just inputs this data 96 by 96 and processes it and runs through. And this is a very big beauty of using like modern deep learning frameworks. Yeah, so this is step 1. You have to load the architecture and make sure the model is compiled with correct input size. I'll show everything in a while, no worries. There's also a second part to learn the pre-trained weights. Oh my god, it's very difficult. You just have to, while calling the model from Torch Vision, you have to specify that weights are pre-trained on ImageNet. Wow, that's very hard. There's also freeze bottom layers. Is probably a tricky part, but even like with Googling for 5 minutes, you can easily find out how to do it on your own. The whole concept of transfer learning, the whole concept of freezing layers from bottom to top, and basically in this task you're supposed to just load a completely ready to go model, make sure it is responsive to your data. Then you have to freeze all the weights. And freeze all the weights, meaning you will not be training this part of the network. I'll just show just in a few minutes. And you only have to change the top layers. Basically, the one I've just showed you here at the bottom. Change fully connected 1000 to fully connected 10, for instance. And that's it, pretty much. Freezing the layers. This is a quite an old concept. Basically, we presuppose, once again, back to discrete mathematics, that our bigger data set, ImageNet, has already more than enough knowledge as to satisfy our needs to classify STL10 and these images. And once we realize this, we don't need to like train anything from scratch. From scratch meaning having a completely naked and empty neural network architecture carcass, take extra 20 to 30 epochs time just to learn something that has been already learned, actually in enough capacity to solve your task. And basically, once you realize this, we go back to the image. Suppose we have like adjusted the input size and everything is good. We have this ResNet, like this part. Let me just select. I'll be showing like this. We have this part, and everything is fine. But what does it mean to only change the bottom layer? Well, we did change this one. We changed like we set up FC10 here, so only 10 classes will be trained. Outputted in the end, right? Like the total sum probabilities will be as of 10 classes. But these old layers, so these ones, so this thing, this we don't need to touch at all. This is why it's called freezing the layers, which is to signify the model that we turn off the gradient flow. We do not calculate anything from there, so the model just simply reuses the data, the knowledge it already has from being already trained back then someone on ImageNet, uses the same data. The only difference is, of course, the output size, the 10 classes, that's for sure, and certainly the second difference is this different resolution. And pretty much this is the same task as ImageNet classification. And that's also kind of makes it much more convenient than as to creating everything from scratch, taking a lot of time. So in other words, just making your time not as well spent. And in this task, in this home assignment, this is basically all it's asked for. You just you have the same data set. You go into deep learning frameworks. Let me show you something. This is. I think it's better if I do this. PyTorch transfer learning. PyTorch has a lot of great tutorials based on CS231 course, which is absolutely insane. I do recommend it very badly to you. It's an insane and cool course, especially the lecture editions from 2016 winter. So yeah, you do is just install PyTorch, you import the needed modules, blah blah. You set up data transformations, you create the data sets, basically in a PyTorch format. You create then data loaders. You presumably define like labels, class names, and you initialize the device, either TPU or CPU, GPU, whatever, CPU, GPU supposedly. Then there is a train model function that they show here. Let's just have a quick breakdown. This is a very simple way. Do you need to train something? I don't remember. Oh, train. Yeah, you need to train, of course. So basically, training comprises of different parts of very bright horizon of deep learning and optimization. So there's an optimizer. It could be SGD, stochastic gradient descent. It could be ADAM. It could be ADAM W with decoupled ATK. It could be rectified ADAM. It could be SGD, by decay. There's a lot of options basically. You have to play around with this and just Google it on your own. Just don't put too much effort in it. It's use something as simple as possible on these assignments. These are not supposed to take too much time. You just set number of epochs according to your ideas, like how much you should train. Don't train too much because you have a very small data set. You barely need to train. There's like almost like 1, 2, 3 epochs. Then you set like a loss function. You create a model, import from Torch Vision. Torch Vision models. Let's see. There's this Torch Vision has a Torch has a great module called Torch Vision, and then you have this great example right off the bat: multi-weight support API. You import models from Torch Vision models module, and you get like ResNet 50 and ResNet 50 weights. See, two different objects. And then you create some old weights model with worse accuracy, ImageNet 1K v1, and then there's ResNet 50 weights, ImageNet v2. And once again, you can also set the default weights. You can pass the string, of course, not import this weird construction that I see for the first time. Or you can use the pre-trained model. This is like the second part of the task. If you're feeling like you want to do some more work, there's also an opportunity for you to retrain from scratch. Just reinitialize the weights, unfreeze everything, and train the total network and see how it works. Yeah, there's also hub, Torch hub, of course. What is this? Yeah, here's an example how to use the pre-trained image classification models. That's exactly what we need. What you need, rather. You get like some weird image, test image, and then you initialize the weights. You then initialize the model and make sure it's trainable by selecting eval or non-trainable. Then you initialize the transforms for the weights. These are supposed to be like explained briefly and importantly here, like here data transforms. So you have one set of transformations on train and one on validation or on test. What's happening here is they do some augmentations here. So they randomly resize and crop the image to this resolution. And then they have a certain probability for an image to horizontally change its axis. And then this part basically is as a must. Without it, the PyTorch pipeline will not work. And basically, what it does is just normalizes the tensors for pixel intensity. And then, of course, on validation, they have some different set of augmentation center crops, resize the tensor. Very nice. I'll show you the general kind of idea of the code in a while, but the ones of mine. But here, see, this is the whole list of weights with different accuracy. This is A1, meaning top one, and a accuracy A5 at 5 equals top 5. This is the one something I've been talking about here. For image classification, there's these two benchmarks, and you can monitor which model you would like to use, the number of parameters it has. So I do urge you to not use some absolutely astounding parameter weights. So I would strongly also encourage you to actually use something very, very simple and small, like MobileNet. It's going to be fast. It's not going to be an overkill in the data set. Just trust me from my experience. You can, of course, like if you feel to use some different ResNets here from 20 million parameters, 25 to 80 million parameters, but that's up to you. There's also ShuffleNet, VGG, SqueezeNet, good old architectures, VAT. This is the version transformers I've been talking about. See how huge they are, like 600 million parameters. This is insane. I know this is like the H14 version, the huge 14 with a patch size 14, but still, this is ridiculous. But they do have impressive numbers, of course. They very much do. And then we have, like, in the end, in the bottom, we have WideResNets, the ones I mentioned also in the beginning. They are much better than the usual ResNets. They also are more or less lightweight, depending on the ImageNet ImageNet constitution of and the architecture. And you can just also press a link, I guess. And this will lead you to GitHub repository for the PyTorch models, and you can also get more acquainted here with the concept itself. There's quantized models that are very much optimized and have less weight and less parameters, because for quantize a deep learning model means to rid it of unnecessary floating points for different neurons. Not all of them, of course. So instead of float 16, for instance, the model is recalibrated to unsigned int 8, and then it works fine. But you have to be also careful with that. There's these different models here. See, they're much more lightweight, while still showing decent accuracy, I guess. So yeah, this is semantic segmentation already. You get the idea. I don't know. Let me see if I can send this in chat, just for simpler for you to look. And then, last but not least, there's this. Yeah, once again, I'll reiterate. There's a bonus task to retrain a model from scratch. All you have to do differently from this part is just to not freeze. It is even simpler. But this can be harder in terms of like finding the correct set of parameters, hyperparameters, activation functions, I don't know, schedulers, etc. for the network, and for it to converge better. But still, you have to like write a couple of sentences on how it compares with the previous approach, with like transfer learning, and that's pretty much it. This part, you're free to do it if you like, if you will. And this will save you time on the next week, because you'll need to complete this in any case. Basically, this is not too complicated. There's just two architectures being compared. The convolutional nets that have been on the lecture and that I've been explaining here, also two vision transformers that have a different concept that comes from different area, but basically there's this paper. I think I have this now. Oh, this WideResNets. This paper, you just have to read it. Do vision transformers, ViTs, see like convolutional neural networks. And there is like a couple of dudes discussing whether basically, this is pretty fresh actually. This was updated recently. They are discussing if like the learning capacity of transformers is as good as convolutional nets, or vice versa. So basically, both have downsides and upsides, and now a lot of different versions of ViTs are coming out. And I made like whole lectures on them in different institutions, and I like did breakdowns and reviews. And this is a very promising architecture, obviously. It's still not quite as fast as CNNs in production and inference, but still, you just have to very briefly read the paper, see the methodology, how they compare to approaches. So some nice little heat maps or something, some plots, see how they compare, and write your observations on the method of comparison. And by that I mean you have to indicate like what questions are being studied. It's a very hard question. And then there's how the networks are compared, the methodology, and the conclusion of the paper, probably somewhere in the bottom, before appendix, before the references. There's this cheat code for you, this conclusion. You have to concisely write something about conclusion. But this is optional. This is I do not encourage you to do this like absolutely in a must way of a manner right now. You have your time to prepare if you want. But if you're ready, you can submit this as well. Yeah, last thing I wanted to basically show to you is my own solution for this home assignment last year. This is the same data set reading of STL10, checking the images, reading labels, very nice. And then just I did this in PyTorch. I wasn't that good at deep learning, like hands-on back then, but still. I think I was using EfficientNet, maybe something different, we'll see. So just importing all the different vital modules to get the training started. There's a data loader, a data set from utils, and torch vision for the model, and then transforms from torch vision ST. That's also a very classical way to import it. And then create a custom data set. Wait, what? Did I use this? Oh, I see. This was a placeholder. So you have to wrap your dataset. If you're using PyTorch, for instance, you have to wrap this into a module inside the PyTorch library, which is called dataset, torch dataset. This has to have like an init method, like a built-in feature descriptor. It's very hard. I'm sorry, it's like 2 p.m. already. Start someday. So you have an init method that just reads data from some source. It could be a CSV, it could be a data generator, a flow from directory, whatever. Then transform is a transform that you have to pass as this just is applied to your dataset when you feed it into the model. Then the length is basically just the number of images. And the get item is some way of you to return the pair image label pair. It's not too hard. And basically then you indicate the image size, you do this pre-processing, this good old well-known thing, the one that is here. These you can do this in two ways. You can do this in a very weird way that I did. You can do this in a proper way, like data transforms with composes. But in any case, it's fine. Just do some augmentations on your dataset if you want to. Superficially inflate it to improve the convergence of the network, and just stack this up, normalize, blah blah blah. Some validation transforms as well, and then you create the objects, the transforms, the ones very important, dot compose, the train transformations and validation transformations, and then you create a train data from a custom data set, and then you create a data loader, also an important module, from an existing train data, which is a custom dataset, torch dataset. You also specify batch size, how many images are going to be fed into your neural network per each time step. Usually, the more the batch size, the higher the batch size, the higher learning rate is supposed to be. And vice versa. If you have a batch size of 1, you have to be very careful with your learning rate. They are inverse, they're like inverse proportional. So meaning that if you have a high batch size, for instance, 512, you get like a big chunk of information and you process them in one go. And this means we cannot like pay enough attention to each image and extract enough features from them, which means the model is going to be underfitting over time, unless we balance it out with a learning rate, a higher one, that is going to make bigger steps and converge the model better. And of course, if we have a batch size like of 4 or 2, like let's say 4, then the model is going to actually very attentively have a look at each 4 images per each time step and like retrieve a lot of information. And this can be bad because the model can overfit, can learn the features that do not like exist in the pattern of the data set. But you can cancel this out, of course, by using a very low learning rate, by making very small steps towards the global minimum, optimum, and like balance your training like that. This is also kind of an interesting concept I wanted to introduce. Yeah, you create data loaders for validation as well, and then I did this. I couldn't find back then for some reason the EfficientNet implementation in the official Torch Vision module. So I instead installed the library called EfficientNet_PyTorch, and I used it uses the same infrastructure, the same API, but just it was easier that way for me back then. Just call an EfficientNet and use it from pre-trained EfficientNet B0, and then also you make a summary to make sure the model is going to be fine. Summary is like also another library that is installed for PyTorch to monitor what your model looks like with certain data set. You just pass in the model, the EfficientNet, for instance, this one, EfficientNet B0. It's a decent model. It's not as good as BSAN, it's much tinier, but it's fine. And the input size, note that the channel order is different, it's inversed. In PyTorch, first come channels, then heights, then width. So CHW. In a normal notation, it usually comes like this. Normal notation now. Normal notation is it's actually WHC. In PyTorch or just Torch, it's CHW. Well, TensorFlow can be specific as well, I guess, but you can all Google that up if you are ever getting any errors during the training. And then it shows you like how layers are adjusted, how much processing is done, the features of the model, how many parameters, 5 millions only, etc. And then you can have a look at the model. This is like all the inside, like the under the hood, what's going on. First we have convolutional stemming part with zero padding, then batch norm, then like a set of MBConv blocks, a very novel thing, unique to EfficientNets. Not only them now, but still. Back then, yes. Squeeze excitation, expand, reduce some attention, like things. And then there's also this repetition, block 4, block 5, and then it's always called until infinity, block 15, and then we have convolutional head. See, this is the part that finalizes the feature extraction part of the pipeline. Final batch norm, average pooling, and drop out something. Neurons for simplicity's sake. And then there's fully connected linear with input features of 1280, output features 1000. This is bad. This is not supposed to be the case for you, because I have not changed that yet. This has to look like out features equals 10. Only then will it actually work for your dataset. And then, as you can see, I just created a device, which was a CPU for me back then. I have a look at my fully connected module. I just call a reference to my model object and call an underscore FC part of the module. It shows in features, out features 1000. That's not good. And I just read its summary. And how do I freeze layers? Well, basically, in PyTorch it's pretty simple. And in TensorFlow it's also simple. You just iterate over all the model's parameters, and you set requires correct false. You can now say, like, you may say now, hold on, this freezes the whole model. Yes, it does, but it freezes everything that we don't need and need, but we can explicitly make sure we do not refer to this part. We just replace it, the FC head, classification head. And then you import the same like torsion and modules linear layer. Fully connected is just a linear layer that maps 2080 to 10 now. You set bias true, and you reassign the layer of the fully connected part of the network. And then you just optimize, set optimizer, train, blah blah blah. And this is how it looks like, pretty much. Yes. Now to your questions.
I have a more like basic question about the pooling layer. So is that how it reduces the resolution of the image, right?
Yes.
And it also increases the number of features or something like that.
Yeah.
So how does that work? Why does it increase the number of features?
It increases the basically by dividing over like a factor of 2. A typical example of an average pooling or max pooling, it has a kernel of size 2 by 2. And if it does apply the 2 by 2 operation of pooling, if one applies such operation to any certain like image representation, for instance, a full image or a processed image, it appears as though the pixels, the feature maps are actually doubled from the previous run, because it's supposedly and presumably it does multiply the it fixes and reinstantiates the trade-off between the feature maps and the spatial resolution of the image. So the less it is applied not only to your image, right, in this very specific moment, also is applied to all the previous feature maps. And once it's applied, it basically just slices them down into in 2 times, and then it yields us more feature maps while we sacrifice the spatial resolution, the height and width. Hope that was
Okay.
clear.
Okay, thank you.
Anything else? Take that as a no. So you have your assignments. You always know how to reach out to me in case you have any difficulties or questions, either in Slack or on Telegram if someone knows it. So I do wish you a very productive week after the weekend, and we'll see you guys in a week. Bye-bye.
Goodbye.
Yeah, cheers.